So with the last lecture, we are actually declaring success in terms of designing controllers. We use pole placement, we check controllability, and off we go. The big problem, though, is, well, we don't have x. And we have to, when we do, u is minus kx. Well, x is there, but we don't have it. So what about y? Ultimately, we don't have x. We have y coming out of the system. And somehow, this y has to translate into a u. It's not enough to say x translates into a u, because we actually don't have y. Well, here is the cool idea. I'm going to put a little magic block here. And the output of that block somehow should become x, meaning I would like to be able to take y, push it through a magic block, and get the state out. Now, I'm not going to get x exactly. In fact, I'm going to put a little hat on top of it. This is my estimate of a state, meaning I'm taking my sensor measurements, y, and based on those measurements, I'm going to estimate what x is, and I'm going to call that x hat. And in fact, the magic block, the thing that allows us to get x from y, is called an observer. So in today's lecture, I'm going to be talking about these observers and how do we actually design them. Well, it turns out that the general idea behind observer design can be summarized in the predictor-corrector, under the predictor-corrector banner. So let's say that we have x dot is ax. Forget about u for now. That doesn't matter. And y is cx. Well, here is the idea. The first thing we're going to do is we're going to make a copy of this system. And our estimator is going to be this copy. So I'm going to have x hat dot is equal to a x hat. So my estimate is going to evolve according to the same dynamics as my actual state. And this is known as the predictor, which allows me to predict what my estimate should be doing. But that's not enough. What I'm going to do now is I'm going to add some kind of notion of how wrong or right the estimate is to the model. And one thing to note is the actual output is y. The output I would have had if the state was x hat is c times x hat. So I'm going to compare y to c times x hat. And in fact, what I do is I add a piece to my predictor. So x dot is ax, or hat, plus this difference, y minus cx hat, which tells me how wrong I am. And then I add some gain matrix here, L, and this gives me a predictor and a corrector. So this part here is the predictor, and this part here is the corrector. And this kind of structure is known as a Leuenberger observer, named after David Leuenberger. But the point is that when you have this predictor-corrector pair, you have some way of, hopefully, figuring out the state, or at least a good estimate of the state, from the measurements y that show up here. So the only question now, well, one question is, does it work? The other question is, what is this L? So the first thing we should ask is, how do I actually pick a reasonable L? Well, the first thing we do is, let's define an estimation error, E, as the actual state minus my estimated state. And I should point out that we don't know E, because we don't know x. But we can still write down E is x minus x hat. Well, I would like E to go to 0, right? Because if I can make E go to 0, then x hat goes to x, which means that x hat is a good estimate of x. So what I would like to do is actually stabilize E, make E asymptotically stable. So what we need to do first is write down the dynamics for my error equation. So E dot, well, that's x dot minus x hat dot. Well, x dot is just ax. And x hat dot, well, we have this form, right? The ax hat plus L, y minus cx hat. And then we get the minus signs in front of everything. So this is my estimation error. Now, y is equal to c times x, right? So what I actually have here is E dot being a times x minus x hat minus LC times x minus x hat. But x minus x hat is E, so E dot is A minus LC times E. This is the dynamics of the estimation error. We don't know E, but we know that this is the dynamics. So what we need to do now, of course, is pick L in such a way that the eigenvalues to this matrix, A minus LC, have negative real part. Because if we've done that, we've stabilized the estimation error. And I wonder how we should go about doing that. Actually, I don't wonder. We know how to do it. Pole placement. We know how to do control design. This looks just like control design, but it's actually observer design. Well, we want the real part of the eigenvalues to A minus LC to be strictly negative. So let's just pole place away. Okay, so here's an example. X dot equal to this, Y is equal to that. Fine. Now, I want my error dynamics to be asymptotically stable. So if I write down A minus LC, and I should point out that in this case, C is a 1 by 2. That means that L has to be a 2 by 1, because these things have to cancel out, and I get a 2 by 2 left. So L is actually a 2 by 1 matrix in this case. So if I write down what A minus LC is, it becomes this semi-annoying matrix, but at least we know what this matrix is. What do we do now? Well, we compute the characteristic equation to A minus LC. And if we do that, we compute the determinant of lambda I. So this is the determinant of lambda I minus A minus LC. Right? So if we compute that, we get the following expression. Well, now we do what we always do in these situations. We pick our favorite eigenvalues, and it seems like I am very, very fond of lambda is equal to -1. If I do that, I get this as the desired characteristic equation. Well, what do we do now? Well, we line up coefficients, of course. These coefficients have to be the same, and these coefficients have to be the same. And if you actually solve this, I'm not going to go through the algebra. I encourage you to do it on your own. You get that L1 is -2/3, and L2 is 1/3. And in fact, the way this would look, my observer gain is, well, L1 was -2/3, so here's L1, and L2 was 1/3, which is there. So my observer dynamics is x dot is, well, x hat dot is ax hat plus, this is L, times y minus cx. So this is my observer dynamics. What I'm showing here in the plot, in blue, this is x1, the actual x1, how it's evolving. And in red, you see my x hat 1. And you see that after a while, they end up on top of each other very nicely. Similarly, in the right figure, in blue, you have x2, and in red, you have x hat 2. And as we can see, the state, the estimated state, x hat, does indeed converge to the actual state. So here is what's going on right now. I have x dot is ax, y is cx. Out of this thing, I can suck y, right? Because that's what I'm seeing. These are my measurements. What I'm doing now is I'm feeding this y into my observer that has a predictor part, which is the dynamics, plus a corrector part, which looks at the difference between the actual output and what the output would have been if x hat was my state. And then out of this comes x hat, which means that we have some way of figuring out what the state of the system is. Now, obvious questions are, well, there's only one question, actually. Does this work? And the answer is no. It doesn't always work. Just like pole placement doesn't always work when you're doing control design, for the same reason, pole placement doesn't always work when we do observer design. And what we need is we need something that's related to controllability. So controllability tells us, do we have enough control authority? Are our actuators good enough? Well, for observer design, the concept is known as observability, which means, do I have a rich enough Y, meaning a rich enough sensor suite, so that I'm able to figure out what the system is doing, meaning estimate X from Y. And the topic of the next lecture is exactly this, observability. When can we indeed figure out X from Y.